Okay, so we continue to talk about Hamiltonian analysis for this model of gravity couples to dust, because we are going to use the dust to extract the physical, to extract the reduced phase space, to come to remove the constraint and come to the reduced phase space. Hamiltonian analysis. So here I'm not going to give you a detailed Hamiltonian analysis, but just give you the result. Okay, the Hamiltonian analysis. Well, something you can imagine is that you will get canonical pairs. So firstly, the gravity canonical pair will be the same as before, but now you will have canonical pairs for dust, for the matter degree of freedom. But here, since rho and w, they are just Lagrange multipliers, and in the end, you are going to solve them in the Hamiltonian analysis. And the canonical, the physical variables, the physical degree of freedom for this model is only t and s. So those t and s, they are dynamical degree of freedom. So which means that they will give you canonical conjugate variables. Well, rho and w, they are just Lagrange multipliers, so they are not associated with conjugate pairs. Okay, so now you get conjugate pairs. So firstly, the conjugate momentum for t is called p. So it has the natural Poisson bracket with t. And the conjugate momentum for Sj is called Pj. Okay, so these are the only two Poisson brackets. Well, so you have position variable t and s, and you corresponding to conjugate momentum p and pj. Okay, and these are the conjugate pairs in addition to the gravity conjugate pairs g and p, the metric and extrinsic curvature, or Ashitaka connection and sensitized triad. Yeah. So depend on the framework for the gravity. Okay. And also the Hamiltonian, the total Hamiltonian is still the linear combination of constraints. Yeah. Although here you have matter degree of freedom, no matter what kind of matter you put in the end, the Hamiltonian of the couple system is again a linear combination of constraints, very similar to the pure gravity case. Hamiltonian constraint will be, so here it will be, I will call the total Hamiltonian, because this is a coupled system. V3x. And C total CA total. Okay. So what is this C total? Equals to C. C is just the gravity, so I will call C just the gravity part of the Hamiltonian, plus the matter part. This matter part, you can see it is very simple. It is P square root 1 plus QAB CACB. Here, CACB is just a diffeomorphism constraint for gravity, for pure gravity, divided by P squared. Okay, so this is the total Hamiltonian constraint, which supposed to vanish on the constraint surface. And you have total diffeomorphism constraint. This is C, A, the gravity diffeomorphism constraint plus the matter part. P partial A T plus okay, so you can see that although the gravity part of the Hamiltonian, it is non-polynomial, it is complicated, but the matter part is relatively simple. So P is just a conjugate momentum for P. So you can see this is, so the matter part depends on P, it is very simple. And the matter part for diffeomorphism, it is also linear to P. So now you can actually solve them. So you ask your constraint to be 0, you can solve these two equations. And they can be solved. Well, they can be solved. They can solve for P. Yeah. So you can solve this constraint for P. You can solve by P equals to something H, something called defined to be H, and it is this H is this guy, C square QAB C. So if you ask P equals to this, and it is the solution of the equation, constraint equation. And similarly, you can solve for Pj from the diffeomorphism constraint minus Saj Okay. Right. And what is this Saj? This Saj, it is the inverse matrix. The inverse of partial A Sj. Okay. So you can imagine that this, if you view, as I said before, this Sj will be just your ruler, just your space parametrization. Yeah. The matter, the dust field Sj will be your space parametrization, and this Sa, this partial A Sj, it is just like a Jacobian, right? So this Sj is, suppose Sj is your new coordinate. Yeah. But of course, this new coordinate has physical meaning. It is just the value of the dust field. But suppose you view Sj is just some coordinate, and then the partial A Sj, it is just a Jacobian, right? For your coordinate transformation. Yeah, then it is realistic to require that this partial A Sj is non-degenerate. If you view Sj is a matter coordinate, matter reference frame. Okay, so now you can see that because the Hamiltonian constraint depends on matter, the matter part of the Hamiltonian constraint is very simple. So you can actually solve the matter degree of freedom. You can solve those constraints for the matter degree of freedom for those P and Pj. Yeah, okay. You can solve that. And moreover, what you another way to say this is that you can define. So what do you mean by solving those constraints? By solving these constraints, what you actually do is you can also understand by you can understand this as giving equivalent constraints. Right? You are actually I can define equivalent constraint C equals to P minus H, which is again equals to 0 on the constraint surface, because this is the solution of constraint, and C twiddle J equals to Pj plus Saj T. Again, this is the equivalent constraint. Yeah. So you can see these two constraints, they are in some sense equivalent constraint of the earlier C total, yeah, C total and CA total, yeah. And now these constraints, yeah, it's simply depend on P in a very simple manner. And also because the dependence on P and Pj, and these constraints are actually abelian. They are abelian constraints. Constraint, what I mean by abelian constraints, it means that so suppose I call this C mu below x. Okay. So the Poisson bracket of this C mu x, C between C and Cj, or between Cj and Ck, and between C and C, they are all zero. The Poisson bracket, they are all zero. C mu x, C mu x prime Poisson bracket equals to zero. Yeah. You can just check them by concrete computation. So these constraints, the constraint algebra for these new constraints, which are equivalent to the earlier constraint, in some sense equivalent. Well, if you solve them, you can see that they are not exactly equivalent, and up to a certain sign factor. Yeah. They are technical details. I'm not going to talk about it. If you are interested, you should look at references. But so roughly speaking, these abelian constraints, they are equivalent to earlier constraints up to some subtlety. But these new constraints, they are really abelian. They are abelian. They satisfy very simple constraint algebra. And the constraint algebra, it is a Lie algebra, and it is abelian, trivially abelian Lie algebra for these new constraints. That's why these constraints, these new constraints are interesting. And well, essentially, it is because those new constraints are actually solutions of the constraints. So that's why they are. That's why they are interesting. This new constraint just tell you the solution of the earlier C and C total is just the P equals to H and Pj equals to this gadget. All right. So now you see you can actually, by using the method degree of freedom, you can actually solve the Hamiltonian constraint and deeply mobile constraint. Okay. So now when we solve those constraints, you can see, well, you can view that the solution of the constraint is a constraint surface. It's a parameterization of constraint surface. Well, recall our figure. So firstly, we need to find the constraint surface, namely by solving the constraint. And secondly, we have to parameterize. We have to find those gauge orbits, and we have to quotient the gauge orbit and find the reduced phase space. Okay, and how to find those reduced phase space. All right. So let's construct Dirac observables. So we need to find a way to construct all possible interesting Dirac observables, namely gauge invariant observables, or namely functions on the reduced phase space. Functions on reduced phase space. Okay. Okay. So now how to construct them? So now for any, so let me consider an arbitrary function f on the unconstrained phase space. Unconstrained. Okay, so let's consider an arbitrary function on the unconstrained phase space. Okay, and you know, suppose this is the unconstrained phase space, and you have gauge transformations running on the phase space, so it gives gauge orbits. Right? Okay. So you have gauge orbits. Because this is unconstrained phase space, we haven't modeled the gauge yet. So let's consider an arbitrary function on this unconstrained large phase space, and we consider a gauge transformation act on this function. Okay, so it depends on some parameters beta. It has, because we have many constraints, several constraints, and it depends on several parameters beta. Let's consider a finite gauge transformation. finite gauge transformation generated by Hamiltonian constraint and diffeomorphism constraint. And what is this finite gauge transformation? It is actually because the gauge transformation give you a diffeomorphism, right? Give you diffeomorphisms on the phase space. The gauge transformation it is just a, if you view this phase space as a manifold, and these gauge transformation they are generally gauge orbit. They are just some one parameter group or multi-parameter diffeomorphism group running on the manifold of the phase space. This is not the actual diffeomorphism on space-time. They are diffeomorphism on the phase space. So then when you have diffeomorphism, you just pull back the function. It's just a pullback map acting on the function generated by diffeomorphism. So these are diffeomorphism groups. Group on phase space generated by the linear combination of Hamiltonian constraint and diffeomorphism. Or more precisely here is generated by this abelianized Hamiltonian constraint and diffeomorphism constraint. Because the abelianized Hamiltonian constraints, they are equivalent to the in some sense equivalent to the Hamiltonian constraint and diffeomorphism constraint, the total Hamiltonian constraint, diffeomorphism constraint, and those they are again first class because they are just abelian. Of course, they are first class, and they generate gauge transformations, just similar as before. And those gauge transformations give gauge orbit, and this gauge orbit, these gauge transformations, they are diffeomorphisms on the phase space. And then you can talk about the pullback of function or diffeomorphism act on function, and so on. And or in ordinary language of field theory, when you have gauge transformation of variables, then of course it gives diffeomorphism. They give you gauge transformation of arbitrary functions, because arbitrary functions are functions of variables of your fields. All right. Anyway, so this is, let's consider gauge transformation of an arbitrary function on the unconstrained phase space. Okay. So then this function you can define, if we can construct a Dirac observable, I call it f, tau, and sigma. So this will be a Dirac observable. So how to define this? This is defined to be the gauge transformation. So firstly, the gauge transformation of this function, similar, the same as above, but with certain parameter, with a specific parameter beta, satisfying another equation, namely the gauge transformation of function t, which is your dust field, equals to tau, and the gauge transformation Sj equals to sigma j. Okay, that's why the Dirac observable in the end, it depends on tau and sigma. Yeah? The Dirac observable here, it is a function of tau and sigma, and how tau and sigma enters the formula, it is the gauge transformation of the dust field tau with the parameter beta equals to tau, and the gauge transformation of the dust field Sj with the parameter beta equals to sigma. Okay. So, and then these two equations actually solve this determined beta. This determine. Actually, if you can just try it out and write down explicitly alpha beta t. You just use this this linear combination of constraint act on dust field T, it is very easy to calculate because these constraints are linearized. It's just linear to P, and all the other parts just commute with T and S. Okay, and you can explicitly write down this expression, and in the end, this is just a translation. This gauge transformation of T and S is just the translation of T and S. So, and then when you explicitly write down gauge transformation of T and gauge transformation of S and plug in this formula, and you can actually explicitly solve beta. You get beta equals to tau minus T. Well, beta is a field. And it's just like C and Cj is a field depending on X. Okay, so here it is beta 0 X equals to tau minus Tx. Vector beta X equals to sigma minus S X. Okay. So if you explicitly write down this gauge transformation of T and solve these two equations, you just get beta. Well, it's just a translation of T. Okay. And so here you can see that this beta can be explicitly solved by using T and S and tau and sigma. Okay, and you plug in the solution beta into alpha beta act on F, then you explicitly get the value of the Dirac observable. That's why this Dirac observable is just a function of T and sigma. Okay. And so this is the definition of Dirac of this F, and then you get a property that F, tau, and sigma is the Dirac observable. Dirac observable. Okay. So I mean, by first looking, you may have some little trouble about understanding why it is defined this way, but it will become clear in a moment. Maybe I can just explain a little bit at this stage. So here, this is just you see, you are really just using T as your time, as your clock, and S as your ruler, because you are when you make gauge transformation of T. So this is something like a gauge fixing. You make a gauge transformation to fix T to be the value of tau. Fix your clock. You call this clock the value of the clock to be tau. Yeah? And you just fix your gauge. You ask your arm of the clock. Yeah, at some point you call this 0. This is well 12 p.m. or 12 a.m. And this is something like you fix the gauge. You are actually making a gauge transformation. So fix your arm of the clock at the position. You call it 12 o'clock. Okay, and similarly, you make gauge transformation of your ruler. You fix a position in the space. You call that the origin. Yeah, and also or you call it certain value sigma. Yeah, and this is fixing the reference of your ruler, right? And then once you fix this, and then you can use your clock and ruler to measure the value and to parameterize the value of your function. Yeah? And then this is a really then the result is not really then the result is not dependent on the coordinate system, yeah? Because you already fixed your coordinate system by using material, by using the arm of the clock and and your ruler. You already fixed your coordinate by using clock and ruler, and then of course, if you make arbitrary another choice of coordinates, it's not going to change any physics. All right. So okay. So now you can also explicitly check this result is a Dirac observable. Namely, if you compute you can compute C total Poisson bracket with this F. You will get this result weakly equals to 0, and C total A Poisson bracket with F is again weakly equals to 0. So it's enough to be weakly equal because you only work on the constraint surface. So you model out the gauge orbit on the constraint surface, you get the reduced phase space. It's enough to work on the constraint surface. Okay, so here it means that F is gauge invariant on the constraint surface. On the constraint surface, and it is a function. Then because it is gauge invariant, it means it is constant along gauge orbit. Yeah? And suppose the function constraint surface, which is gauge invariant, that means it is constant along gauge orbit. Then you can project this function on the reduced space. You can view this function as a function on the reduced space. So, function. Okay. So this F construct in this way is really a Dirac observable. Yeah. And now let's come to the philosophy behind this construction. Okay. So this F, it is parameterized by value of dust field. By values of dust field. Fields. They are called clock fields. Yeah, I mean, yeah, they are clocks and rulers. Yeah, but well, sometimes we just call them clock fields. Yeah, these clock fields are T and Sj. Yeah. And so we sometimes call the dust reference frame. Because the value of those fields are tau and sigma. They are parameters to parameterize. They are actually parameters to parameterize the Dirac observable. So T here corresponds to physical time tau, and S, this is called the value of S corresponds to physical space sigma. This is the physical time and physical space. Okay. Now maybe give you an example to make it very concrete. Let's talk about the, for example, suppose we use ADM formulation and talk about the canonical variable for gravity QA and QAB x. Yeah. QB x. So this x is space-time x. Let's say x mu. Yeah. It is QAB. Well, the spatial metric QAB. Okay, and now this QAB is a function on the unconstrained surface. This is our previous F. This is a function on the unconstrained surface. Right? We haven't imposed constraint on it yet, but we can act on QAB gauge transformation, yeah, generated by abelian Hamiltonian and De Morgan constraint. QAB x mu, okay, and evaluate the gauge parameter at beta 0 equals to tau minus T x, and factor beta equals to sigma minus S x. Okay, so this is the evaluation of beta, just like here. So because they determine beta in this way. Okay, and the result will be what we call Qij tau sigma. Okay, so here it's not, I'm not using AB, but instead using Ij because we are already in the dust frame. So, okay, I'm going to explain in a moment, in a second. Okay, so now so we can somehow simplify this formula by asking this beta 0 and beta to be 0. Okay, so now we actually can set beta 0 and vector beta to be 0 because if we set, so here I mean, in this original definition, we have beta 0 and beta is just for full generality. Yeah, but we can actually just set the value of the dust field T to be tau and the value of dust field S to be sigma. We set Tx. So it is a definition, it is a setup, it is a definition for parameter tau and parameter sigma. We just ask tau is the value of the dust field T, and sigma to be the value of the dust field sigma. Okay? So this is just a definition of the parameter tau and sigma. Although I mean the original definition is more general, so the definition of tau, it is a gauge transformation of T, and definition of sigma is a certain gauge transformation of S. Okay? And now we can be more specific. We just ask the tau is the value of the field and sigma is the value of the field S. Okay, so now suppose we make this setup, so which means that it's like fixing the gauge, because you can view these two equations, they are gauge fixing, because they are not gauge invariant. This equation is not gauge invariant. If you make gauge transformation of T and S by using diffeomorphism and Hamiltonian constraint, it changes the value. So these are some kind of these two equations are some kind of gauge fixing. So now let's fix the value of tau and sigma, and then once we make this setup, and it means beta 0 and beta vector equals to 0, and beta 0 beta vector equals 0, it means that you don't do any gauge transformation. So alpha beta is just a trivial. It's not really doing gauge transformation. So now the formula becomes much simpler. QAB is mu, and so Tx equals to tau, x equals to sigma. Okay, so now you see what is really going on here in this formula, in this definition of the Dirac observable is actually what is the Dirac observable depend on tau and sigma. It is actually the evaluation of the field QAB at the point x, where Tx equals to tau and Sx equals to sigma. Okay. So so you ask the question, what is the value of the field of your Dirac observable? Located at point tau and sigma. So it actually means that your field located at a certain point, you don't know where, x, and such that the dust field evaluated at that point equals to tau, and as dust field evaluated at that point equals to sigma. So, and that's really the role of dust field and those dust fields, and these are the clock and ruler, and this clock field T tells you that point the time is tau, and your ruler S at that point tells you that at that point X the position is sigma, right? And this is exactly the meaning of these two equations. And then you say your Dirac observable, your field taking value at the time tau and position sigma is your field located at that point where your clock tell you that's the tau and your ruler tells that's the sigma. Okay, so you see probably this the philosophy is much clearer in this formula. Okay, so here you can see that those dust fields really play the role of the material clock and material ruler. So the point is that you are evaluating gravitational field, gravity field at point x, where dust field takes value. Okay, and this is gauge invariant because no matter, you can see this quantity, you define this qij tau and sigma defined this way. If you're making coordinate transformation of x, it doesn't change value, because you do the coordinate transformation where you make the diffeomorphism on your manifold, which changes x, but the dust field changes in the same way, right? And the dust field being a scalar, the value doesn't change. You make coordinate transformation of x, it doesn't change the value of tau and sigma, okay? Because both the field q and t and s, they change, and so these two changes actually cancel each other. Well, namely, the value of the field doesn't change, and the value of field depending on tau and sigma doesn't change under coordinate transformation. And also here, the Dirac observable is labeled by Qij instead of Qab, because AB is a coordinate indices corresponding to x. But now, since you are evaluating the field at the dust coordinate system or dust frame tau and sigma, so here this ij, this is the coordinate index for sigma, for the dust frame. So this is like a coordinate. So this is, or you can view that this is like a coordinate transformation. Yeah, this is a coordinate transformation, so that you transform a arbitrary coordinate, which we call x, to a fixed coordinate, which is tau and sigma. And this fixed coordinate is defined by using a physical dust field. Yeah, okay. And this dust field give you a specific coordinate, and you just always transform you evaluate your field q in this dust reference frame. And because this is dust field, it is physical, it is a material frame, it doesn't change under coordinate transformation, because it's just a field. It's just a matter field coupled to gravity. And this way to construct of constructing Dirac observable, it's called a relational construction of Dirac observable, because you see he's really using the relation between gravity field and the dust field. Yeah, and what we mean, and the philosophy behind of this relational definition is, again, what I said. How to parameterize the dynamics of anything, right? And what you parameterize of dynamics of any body is you are using the time, right? And how to parameterize time, you are using the arm of the clock. Yeah, so which means that you are actually parameterizing the dynamic of